m, that will give you m squared v squared divided by m. So 1 by 2 pv is nothing but mv is nothing but p. So you can write 1 by 2 p squared by m. So p squared by 2m is nothing but kinetic energy. Now I will write p in terms of operators. So p in terms of operators. Yesterday we looked into this operator, correct, in the last video. P operator can be written as minus IH cross partial d by dx del. Okay, now p squared, we need to have only p squared. So p squared will be minus IH cross del multiplied by minus IH cross del. You should never go with the square. For operators, linear operators, we should never go with the squares. We should always multiply with the same term. Okay, it is not a plus b whole squared is not equal to that, the formula will not work out. A plus b multiplied by a plus b. Okay, I will say more about later. So this has to obey commutator law. We will see later. Okay, so p squared equals minus IH cross del minus IH cross del, that will give you minus minus plus. So I squared minus 1, that will give you minus h bar squared del squared. So first term, see, look at this one. P squared equal to minus h bar squared del squared, and p is just look at this term, it is the same. So we can say that this first term in equation 1.39 represents the kinetic energy of the particle. Okay, now we are going to obtain the expression for kinetic energy operator. We will see. So we know that psi of r comma t equal to psi of r e power minus I omega t. We know already. So here this equation, we know already this equation, which is nothing but psi of r comma t. So psi of r comma t can be written in terms of psi of r e power minus 1. So you can write psi of r comma t exactly in this expression. So minus h bar square divided by 2m. You have del square. Okay, this is del square, not p square. Del square psi of r e power minus omega t plus d psi of r e power minus omega t equals e psi of r e power minus I omega t. Okay, just take the right hand side of 1.42. So this is equation 1.42. You just take the right hand side, multiply and divide by minus I omega, multiply and divide by minus omega. We are going to see the expression for total energy. Okay, the operator. We know already P equal to minus I cross del. Yesterday we looked into, correct. Similarly, E equals IH cross partial d by dt. Yesterday we looked into. We are going to get that expression. Okay, we are going to derive that expression. So just take the right hand side. So E multiply and divide by minus I omega, you will get this. Okay. Now what I am going to do is just keep minus I omega alone denominator, the denominator. The psi of r, you pull it out. Remaining term is minus I omega e power minus omega t. Correct? The remaining term is minus I omega e power minus omega t. I can write minus I omega e power minus omega t as differentiation of e power minus omega t. Can I write like this? You just differentiate, it will be minus I omega e power minus I omega t. So both are the same. So instead of minus I omega e power minus omega t, I can write partial d by dt e power minus I omega t. So this equation can be written as like this. Is it okay? Multiply and divide by I. So multiply and divide by I will give you, here you have I, here you have I square. Okay, this I square will be minus 1, so this will go up, minus will go up. You have E. So E, you will have I square. So E I psi of r partial d by dt of e power minus I omega t. And earlier I said the eigenvalue of the momentum P equals h bar k. Similarly, the energy eigenvalue is nothing but h bar omega. So you should remember these two eigenvalues which are very important in quantum mechanics. The energy eigenvalue is nothing but h bar omega. The momentum eigenvalue is nothing but h bar k. Okay, one is h bar k, another one is h bar omega. So you substitute E equals h bar omega. Omega gets cancelled. Okay, so you have hi psi of r partial d by dt e power minus I omega t. Any doubt in equation 1.45? So this psi of r, this is dt. Okay, this dt. So this is a constant. Correct? This is a constant. I can take this constant inside or outside, doesn't matter. The constant. So I can pull this term inside. So psi of r e power minus I omega t. What is psi of r e power minus omega t? Psi of r comma t. So this equation can be written as I h cross d by dt psi of r comma t, which is nothing but so this one. So which is nothing but E psi of r comma t. Okay. So it implies that E equals I h cross d by dt. So that is the expression for the energy operator. So this is the energy operator. Is it okay? Energy operator. So the expression for energy operator is given by I h cross d by dt. So you should remember. So we know already that kinetic energy term, potential energy term, the sum of these two, that will give you total energy term. They are all operators. V is an operator, E is an operator, your kinetic energy also is an operator. So this is a time dependent Schrödinger wave equation. Any doubt? Now this equation, we know kinetic energy plus potential energy. So sum of these two will give you the Hamiltonian, which you have studied in classical physics. Hamiltonian is nothing but sum of kinetic energy and potential energy. So I can write this Hamiltonian operator. So H operator. So generally we will write this is H operator, which is equal to E operator. So H psi equal to E psi. Is it clear? So sum of these two, kinetic energy and potential energy, will give you Hamiltonian operator. So you substitute here. So you will have Hamiltonian operator H psi equal to E psi. This is the eigenvalue equation. H psi equal to E psi. So Hamiltonian operator operates on the wave function, will give you eigenvalue with a wave function. Suppose if both are the same, what we call this as eigen function. If both are the same, okay, you can choose psi any wave function, and we are going to operate. The H operator operates on the wave function. If you get the same wave function, this is nothing but eigen function. So H psi equal to E psi is the eigenvalue equation. Very, very important. So where E is the energy eigenvalue, psi is the wave function, and H is the Hamiltonian operator. It is said to be an eigen function of the operator and gives us energy eigenvalue. So energy eigenvalue equation. So is it okay? Time dependent Schrödinger wave equation. Now we will go into time independent Schrödinger wave equation. Okay. Time independent Schrödinger equation can be done by means of separation of variables. So we are going to look into separation of variables. Already we studied separation of variables earlier. In mathematical physics, already we studied. Okay, we will see. We are going to separate the term. Separate the term. Here, how many variables are there? Position and time. So two variables are there. We are going to separate the position variable on one side, time variable on that side, using the technique separation of variables. That's all. So we know already this equation. This equation is known as time dependent Schrödinger equation. We know already. Okay, this is known as time dependent because the solution depends on position and time, r and t. Now the psi of r comma t can be written separately, the position part and the time part. We can write like this. Okay, psi of r, the product of psi of r and phi of t. So psi of r comma t equal to psi of r phi of t. You substitute here in this equation. This technique is known as separation of variable. You substitute in this equation. So we will get minus h bar square divided by 2m del square psi of r phi of t. So b psi of r phi of t, e psi of r phi of t. Okay. Now we are going to divide throughout by psi of r phi of t. Look at this equation, del squared. Del squared is partial d squared by dx squared. Correct? dx squared. So your phi of t is constant. Is it okay? It depends only on r. Del squared is nothing but partial d squared by dr squared in 3 dimension. Okay, dx squared dr squared. And phi of t is constant. So I can pull phi of t out. Is it clear? So I can take this phi of t out divided by, I have already told you that we are going to divide by psi of r phi of t. Psi of r phi of t. Similarly here also, v depends only on x, v depends only on r. So phi of t is constant. So I have pulled phi of t out. This side is E operator is nothing but I h cross partial d by dt. Correct? But here these two variables are there, psi of r phi of t. So I can pull psi of r out because it depends only on t. Okay, so E depends only on T. So it depends only on phi of T, not psi of R. So I have pulled psi of R out. This equation is clear. 1 point, shall I repeat? Is it okay? Now phi of T gets cancelled. So you have 1 by psi of R, the remaining term. So here psi of R gets cancelled. You have I gets cross 1 by phi of T, this phi of T, this term, d phi T by dt. Now look at this equation, this expression, 1.54. You have left hand side depends only on R, right hand side depends only on T. See? So we have now separated. So these two equations are, this equation is separated into these two variables individually, left hand side, right hand side. So if this is equal to this must be equal to some constant. Like for example, P1 V1 equals P2 V2 equals some constant. So something like that. So we have separately, we have separated the separation of using separation of variables, and this depends only on R, this depends only on T. So we can equate this one as constant. So we are going to equate this one as a constant as E. So E. So this is equivalent to E, this is equivalent to E. It means, it implies. Okay, now we are going to left hand side, just equate these two, that will give you E. So this is C minus h bar square divided by 2m del square psi of R plus V psi of R equals E psi of R. Correct? Equating these two. So you look at this equation 1.57 does not depend on T. Psi of R alone. You have psi of R alone. Okay, so this is known as time independent Schrödinger equation. So this can be used for solving energy, solving wave function and thereby energy in quantum well problems, hydrogen atom, harmonic oscillator, okay, barrier problem, and all those things. Okay, any doubt? So this is time independent equation. Okay, so now the last concept, which is nothing but stationary state of a system, and we know this equation very well, correct? So just now we have seen this equation, we know very well. You just take a right hand side. Right hand side is nothing but, you just separate this right hand side into, you can write right hand side equation d phi by dt by phi of t, which is equal to E divided by I h cross, correct? E divided by I h cross dt. Can I write like this? Right hand side alone. Integrating on both sides. Before that, you just multiply and divide by I. Multiply and divide by I. So that will give you I squared, so minus is there, so minus EI h bar divided by h bar dt. Now you integrate on both sides. So d phi by phi of t, that will give you log phi of t. When you integrate dt, that will give you answer t. So minus EI by h bar into t. Okay, raising on both sides with exponential, that will give you phi of t, which is equal to e power minus EI by h bar into t. So we have found out phi of t. Psi of r comma t equals psi of r phi of t. We know already. Psi of r comma t equals psi of r phi of t. So we have found out now phi of t. You substitute in this equation. Okay. So psi of r comma t equals psi of r e power minus EI by h bar t. Okay. Anything? Any doubt? Can you remember this one? We have already used this one earlier. We have already used this equation earlier. E equal h bar omega. Okay, so E by h bar equal to omega. We have already used this equation, psi of r e power minus I omega t. It's the same thing. Okay, so now this is for one particle, one quantum system. For number of particles, number of electrons, okay, number of quantum particles, we can write psi n of r comma t equals psi n of r e power minus E suffix n divided by h bar into t. And yesterday, in the last video class, we looked into this linear combination of individual functions. Can you remember? Individual. Total system can be written as individual basis. Total system can be written as individual basis. So this can be written in terms of linear expansion function. So this is the expansion coefficient. This is for the individual particle. So I have written exactly like this. Okay, now you substitute psi n of r comma t can be written as psi n of r e power minus E n by h bar into t. Take the complex conjugate. You just take the complex conjugate. Our idea is to find out the stationary states. Okay, so that was the topic. Okay, so just take the complex conjugate. Taking the complex conjugate will give you this expression, correct? So an, so this will always taking the complex conjugate, you will have to go with another index. So am star, psi m star r. So now take the complex conjugate, that will give you minus becomes plus because I is there. Your en becomes em. When you take the complex conjugate, don't forget your n becomes m, another index. Okay. After that we are going to apply n equals m, usually that is the procedure. So psi n becomes your psi m star. So you are going to take the complex conjugate. Now multiply these two. Okay, when you are going to multiply these two, you will get this expression 1.64. So this is the complex conjugate of this. This is the complex conjugate of this. This is the complex conjugate of this. And we have added these two e power minus en minus em bracket in bracket t by h bar. Okay, suppose if n equals m, this becomes 0. So anything to the power 0 is 1. Okay, so you will get 1. And this term will give you mod of an squared. This term will give you mod of psi n squared. So left hand side you have r comma t, right hand side without r, without t. See, we have left hand side, it depends both r and t. Right hand side depends only on r. So it means this is a stationary solution. It's a constant in time. Time is constant. Time is not there. In this expression, time is there. When the moment when you are going to apply the delta Kronecker delta function n equals m, this becomes exactly like this. So this is known as stationary solution of Schrödinger wave equation. Okay. So this concept, it was predicted by earlier by Niels Bohr in the year 1911. That is, the angular momentum of electron which revolves on the nucleus will be always integer multiple of the first integer, integral multiple of the integer. So this was predicted by Niels Bohr in the year 1911. But this concept was proposed by in the year 1923 by D. Broglie. D. Broglie says that the wavelength which is around the nucleus, will be always integral multiple of the integer. So for example, you just take you just assume that this is the orbit of the electron. Okay, but the electrons do not have orbits. Okay, very important thing. They will have only orbitals. Okay, suppose for example you are just assuming that this is the orbit, and D. Broglie suggests that this is the for n equal to 3. Number of waves equal to 3 means there will be 3 modes here, 3 are there. Suppose if n equal to 4, you have 1, 2, 3, 4. So the wavelength which revolves around the nucleus will be always integral multiple of the integer. So what does it mean? It means that the waves which are revolving around will be nothing but stationary waves or a standing wave. So the formation of wave packets is similar to the formation of standing waves in sound. Here also standing waves. They are talking about standing waves. Here A0 is the Bohr radius of the hydrogen atom. So this is for the hydrogen atom, Bohr radius of the hydrogen atom. And in fact, these are all de Broglie waves. They are all integral multiples. You just count it 1, 2, 3, 4. You just count it will be 3. So integers, they are all integers. So integral multiple of first integer. So this is the concept. This concept clearly goes with the ideas about the stationary solutions. So we have only stationary solutions. So stationary solutions are there around the nucleus. So this is what we'll have to assume. Okay. So we'll wind up today. Very important question, as I said earlier. This question will appear in the examination. Okay, for 10 mark question. Thank you, students. Bye.